Okay, so in this video, we're going to continue talking about functions, and in particular, we're going to talk about composition of functions and inverses of functions. So let's start with a definition. So let f be a function from a to b, and g be a function from b to c. Oops. So the composition of f with g, or I should say maybe the composition of f and g is the function where the notation for this is g with a little circle of f and then f. So the little circle is not an O, it's a little circle. So g little circle f, which has the domain A and codomain C, and it's defined by g, well, the composition of f and g of x is defined to be equal to g of f of x. Okay. So a few things to notice here. This definition only makes sense if the codomain of f is equal to the domain of g, right? Because if the codomain, if f has codomain b and g has domain b, then this makes sense because for any x in a, f of x will be in b, and so g of f of x is defined. But if the codomain of f doesn't match up with the domain of g, then it's not going to make any sense. So you have to have these things matching up, or otherwise you shouldn't write the composition of f and g. Okay, so in particular the order matters, right? So if I write g composed with, or the composition of f and g, this is not the same thing as the composition of g with f, g and f. In particular, these might not even both be defined. Okay, so let's look at an example. So let's say that f goes from the reals to the reals, and it's defined by f of x equals 2x plus 5. And let's say that g maps again from the reals to the reals, where g of x is equal to x squared. Okay, so in this case, actually the codomain and all the domains and codomains are just the real numbers. So we can actually take the composition of f and g, and we can also look at the composition of g and f. So first, if we take the composition of f and g of x, so by definition, this is going to be g of f of x, which is, so you take f of x squared first, and then you take g of f of x. So if you think about it, it's going to look like this, right? So f of x is 2x plus 5. G of anything is that thing squared. So g of f of x will be the square of 2x plus 5. Now, if I look in the other direction, we take f of g of x. What that means is we're supposed to apply the function g first to x, and then apply the function f to g of x. So if we do that in that direction, what we're going to get is 2x squared plus 5. Okay, so we can see that these are not the same thing, right? These two functions are different. So therefore, when you do function compositions, the order is very important. So if I do f first and then g, or g first and then f, those are different things. And in particular, like I said, the domain and codomain are very important. So it might be the case that these things are not even both defined. So for example, suppose I take f mapping from the naturals to the reals, defined by f of x is the square root of x, and g of x maps from the reals to the naturals, or to, let's say, the integers, by taking g of x is the ceiling of x. Okay. Now, if you think about, these two different compositions, f composed with g, or the composition of f and g or the composition of G and F. And one of these makes sense and the other one doesn't. Here's how you can tell which is which. So in this case, the codomain of F matches with the domain of G. So this one makes sense. The first one makes sense, but the second one is undefined, right? Because I can't apply G and then apply F, because if I apply G, I'll get an integer, but it might be a negative integer. And F of a negative integer is not defined because the domain of F is all the positive integers. So you can't really apply G and then apply F. In this case, if I look at this composition, this is going to give me, so first what I do is I square root x, and then I take the ceiling of the result. So this is equal to this for all x in the naturals. Okay. So this is how function composition works. You basically just apply one function and then you apply the other function. Now let's kind of connect this to some of the stuff we saw last time with injections, bijections, surjections, etc. So, oops. So this is proposition 7.6.3. So let f be a function from a to b, and g be a function from b to c. So I'm going to state this in a slightly different way than in the notes, but what I'll say is if f and g are injective, then so is the composition of f and g, and also if f and g are surjective, then so is the composition of f and g. Okay, this turns out to be basically the same thing as what is being proved in this proposition. Okay, so proof. So let's suppose that, let's prove the first statement. If f and g are injective, then so is the composition. So suppose f and g are injective. Now let x and y be in A, which is the domain of the composition of f and g, and suppose that the composition of f of g applied to x is equal to the composition applied to y. Okay, what we want to prove is that x is equal to y. Well, so this is the same as saying that g of f of x is equal to g of f of y, just by definition of the composition. But since g is injective, this implies that f of x equals f of y, since g is injective. But then this implies that x equals y, since f is injective. So this is the things I've written in parentheses are my reasons for these implications. So therefore, we've shown that if the composition of f and g applied to x is equal to the composition of f and g applied to y. So if those two things are equal, then x equals y. So the composition of f and g is injective. Okay, so let's prove the second part, which is about surjectivity. So maybe I'll just erase this and then replace it with the surjective proof. Okay. So now suppose f and g are surjective, and now let y be any element of C. Remember, C is the codomain of the composition of f and g, because it's the codomain of g. So by surjectivity of g, we know that there exists z, let's say in B, such that g of z is equal to y. Okay, that's just the definition of surjectivity applied to g. But then also, since f is surjective, there must exist x in A such that f of x is equal to z. Ooh, that's the world's worst z. Let's rewrite that, z. So therefore, if I take g of, well, maybe I'll write this in the composition notation. So if I take the function f composed, the composition of f and g applied to x, that's going to be g of f of x. F of x is z, so this is g of z, and that's equal to y. So therefore, the composition is surjective, because what we've shown is that the range of the composition is equal to the entire set C, where C is the codomain of the composition, because it's the codomain of G. Okay, so now that we have the notion of composition, we can define things like the identity function and inverse functions. So definition, the identity function on a set A is the function. So for whatever reason, the notes use the Greek letter iota. So this letter here is called iota. It's not really important that it's iota, but if you're writing this in LaTeX, it's like / iota. Anyway, that's just the notation used in the book, or in the course notes. So basically iota sub A, or in other words, the identity function on A is the function such that if I apply it to x, it's just equal to x for all x in A. Okay, so it's just a function which maps every element to itself. Now we can define the notion of an inverse. So let let's say f be a function from A to B, and g be a function from B to A. So we say that f and g are inverses of one another, or in other words, that g is the inverse of f, or f is the inverse of g. It doesn't really matter. It's symmetric. If, when I compose them, you get the identities. So if the composition of f and g of x is equal to the identity of x. I should just write that the composition of f and g is the identity on A, and the composition of g with f is the identity on B. Okay, so this is, remember, back when we did functions, we said that two functions are equal if they have the same domain, the same codomain, and if they have the same value on every element of the domain. Or in other words, every element of the domain has the same image. So that's what we mean when we say that these two functions are equal. Same domain, same codomain, same image for every element in the domain. Okay, so back in high school, you probably did things like looking at inverses of functions, but you probably didn't really define it in this way. In particular, talking about compositions of functions, but this is the correct way of defining the inverse of a function. So a natural question is to ask, does every function have an inverse? And if not, which functions have inverses and which ones don't? So it turns out not all functions have inverses. So this is now Theorem 7.8.1. So this says that a function f from A to B has an inverse if and only if it is a bijection. Okay. So let's prove this. So let's prove this direction first. So let's suppose, let's prove this direction first. So I'm going to assume that f has an inverse. I'm going to prove that f is a bijection. So assume f has an inverse g, which is a function from B to A. Well, what we need to show is that f is a bijection. So we show f is injective and surjective. Okay, so how do I show that a function is injective? So for injective, let's suppose, like usual, that so x and y are in A, and f of x is equal to f of y. And then I want to prove that x is equal to y. And in this case, the easiest way to do that is to take this equation here and apply g to both sides. So if f of x is equal to f of y, then g of f of x is equal to g of f of y. However, since g is the inverse of f, so since g is the inverse of f, we have that so the composition of f and g is the indicator function, the identity function on A. So if I take this equation here, then the left side is just the identity function of x, and the right side is just the identity function on A of y. So therefore, x is equal to y, because the property of the identity function is that it maps every element of every element of A to itself. So if I take the identity function applied to x, I get x. If I apply the identity function to y, I just get y. Okay, so f is injective. So let's prove now that f is surjective. So now let y be any element of B. Okay, so just to make this clear, earlier I was showing, so this is the proof of injectivity. Now I'm proving surjective. So I'm proving f is surjective. So what I do is I let y be anything in the codomain, and I want to find an element x that maps to y. So what I'm going to do for that, if you think about it, it might not be obvious at the beginning, but if you think about this for a while, and you think about how inverses work, it's pretty clear what you want to do. So I'm going to let x be equal to g of y. So of course, g is a function from B to A, so x is in A, and so we can apply f of f to it. So f of x, well, that's going to be equal to f of g of y. But again, we can use this inverse thing. So this is equal to the identity on B of y, because the composition of g and f is the identity on B, and this is equal to y. So we started with an element y of B, and we found an element x of A such that f of x is equal to y. So we've shown that f is surjective. Okay. So this proves the first direction of the theorem. So we've proven that if f has an inverse, then it must be bijective. So now what we want to show is that if it's bijective, then it must have an inverse. Okay, so now suppose f is a bijection, okay, and we want to show that it has an inverse. So since it's a bijection, since it's a surjection, f is surjective, for each, let's say, y in B, there exists x in A such that f of x equals y. But also, since it's since f is injective, there must be exactly one x in A such that f of x is y. Because there can't be two different elements of A that map to y, because otherwise, if there were two different elements that map to y, then f would not be injective. So what we're going to do for each y in B, let g of y be equal to x, where x is the unique element of A such that f of x is y. So in other words, so note here that we're thinking of g as being a function from B to A. Okay, then by definition of g, we're going to get that g composed with f is the identity on A, and that the composition of g and f is the identity on B. Okay, so so this is not completely all of the details, but if you go through if if you think about this, you can work out that indeed these things will be true. So perhaps I'll leave that kind of unproven for you. But yeah, basically that's the idea. Okay, just a little bit of discussion of notation. So often we write inverses. So the inverse, if it exists, the inverse of a function f is usually written as f with like a -1 up here. But note that if I write the inverse of f, it doesn't mean negative f, and it doesn't mean, so nor does it mean 1 over f, right? So so this means inverse, right? If somebody writes f with a -1 up there, it means inverse. It doesn't mean negative f, and it definitely doesn't mean 1 over f either. Okay, so let's look at a couple of examples of functions and their inverses. So, so let's suppose I define f to be the function from the reals to the reals defined by f of x is equal to x minus 10 squared. Okay. Now, if somebody told you to find the inverse of this function, then it's a trick question, okay? Because this function doesn't have an inverse, okay? And the reason is because it's not a bijection. In fact, it fails miserably because it's not even, it's not an injection and it's not a surjection either. But if I change this function, suppose I took f to be, suppose I was considering this to be a function from 10 to infinity, the interval from 10 to infinity, mapping to 0 to infinity. Okay, so then this is a bijection. So if you were to check, you'll be able to prove that this is a bijection, similar to how we proved some other function was a bijection in the previous video. So this is a bijection in this case, and we can define its inverse. So how do you get the inverse? Oh, by the way, so here, I should have made this more clear. So I'm defining this function to be the same way as before. So it's x minus 10 squared. Okay, so maybe I'll move this around to make it a little bit clearer. So since this is a bijection, we can define its inverse. So how do you get the inverse of a function? You might remember this from like high school or something. So you can take x minus 10 squared, you can write it equal to y and then solve for y. Okay, so if I do that, I get that like x minus 10 is either the plus or the minus the square root of y. So you need to remember how this square rooting stuff works, right? So if I square root a number, then the square root's not really, or sorry, if I have something squared equal to y, that doesn't mean that, this doesn't imply automatically that x minus 10 is square root of y, because it could also be the negative of the square root of y. But in this case, since x is at least 10, we know that x minus 10 is at least 0. So actually we know that in this case, x minus 10 is positive square root y, okay? By the way, here I'm taking y to be in the range 0 to infinity, and we're solving for y. So what we're going to want is x equals root y plus 10. And once you've solved for x, sorry, when I said solve for y here, I meant solve for x. This gives you your inverse function. So the inverse is going to be g mapping from 0 to infinity to 10 to infinity. Note here, I took the codomain and the domain and I've switched them to get the inverse, defined by g of x is equal to square root x plus 10. Okay. So note here that the domain and codomain are important. Okay. So the inverse would be different if I had a different domain and codomain for f. So maybe let's look at an example like that. So I'm going to take the same function essentially, but with a different domain and codomain. So suppose I take f from the interval -infinity up to 5, maybe open bracket, mapping to, let me think, what's the right range? Oops. So it's going to be 25 to infinity, defined by the same kind of formula. So f of x is x minus 10 squared. Okay. So this is not the same function as before. This is a different function. And let's show that, well, let's find the inverse of this function. Well, first of all, we need to know that this is injective and surjective. It turns out that it is. So maybe I won't go into any more detail on that, but it is injective and surjective. You can check using the methods we've built up in the previous video. But let's show that, well, let's find the inverse. So what I'm going to do again is I kind of take, I take x minus 10 squared, I set it equal to y for y in the set, the interval from 25 to infinity. So this tells me again that x minus 10 is plus or minus the square root of y. But now we have to think about, is it minus or is it plus? Okay. Last time we knew that x was bigger than, x was at least 10, so we were able to take the positive side here. This time x is less than 5, right? If x is in the domain of f, so x minus 10 is less than -5, which is definitely less than 0. Okay, so we know that actually this is always going to be negative. So we need to take the negative square root of y, because x minus 10 is negative. So therefore, we get that x is negative root y plus 10. So my inverse is the function g mapping from the set, the interval 25 to infinity to negative infinity to 5, defined by g of x is negative root x plus 10. Okay, if you double check, you'll see that if I take f of g of x, what you get is x minus 10, or sorry, we want to plug in g of x, so we get negative root x plus 10 in the place of x. And then we have a minus 10 squared, so that's going to be negative root x squared. And this was for x in the domain of g, so x has to be above 25, so it's a positive number. So this is going to be equal to x. So since x is at least 0. So it's, in fact, x is bigger than 25 because we're choosing x in the domain of g. So like, all I'm doing here is I'm double checking that if I take the composition of f and g applied to x, then I get x, okay? And I do. And if you take the composition in the other direction, you'll also get x. So maybe to double check that, so let x be in negative infinity to 5. If I take g of f of x, that's negative square root. So I've got a plus 10 here. And I'm supposed to plug in f of x here. So x minus 10 squared. Now x is a negative number, so when I square root, so if I square x minus 10, that's going to give me a positive number, but when I square root it, I should have negative x minus 10, right, plus 10, which is x minus 10 plus 10, which is x. Okay, if you didn't follow my algebra here, I'm sure you can do this yourself, right? A key thing though is to understand where is x, right? And that kind of tells you how to take things like square roots and stuff like that. Okay, so hope that this video was helpful. I'm I'm also going to put up a bonus video where I'll show you some solutions to some exercises, and I'll see you guys next week.